Then I'll take this rate constant equation. Now let me assume that this equation is derived for this type of second order reaction, right, where A and B are different molecules, uh, and also at various time in the due course of reaction, the concentrations of A and B will not be same at, at different time the concentrations will not be same. So for this type of second order reaction, we derived rate constant equation. This is the rate constant equation. And now I assume that the initial concentration is A mole per liter and this is B mole per liter. Now I'm going to take, let me assume B is greater than A. I've taken B. B is in very large amount. B is taken very large amount than A. Now see what happens, right? You just imagine that you are doing an experiment. You're doing kinetic experiment where A is smaller, A is smaller, B is very large amount. So this equation will get 2.303 by T compared to A. B is very large, very large. Therefore, I omit this A. So this is minus B logarithm B A minus X and A, and compared to X, B is very large. X is concentration of product at the time t. So compared to concentration of B, the X is very small, so I omit X. So I'll write B. Here B gets cancelled. This is minus 2.303 by B into T logarithm A minus X by A. Then K equal to, this is minus, you just invert this term. Okay, I'll go step by step. Logarithm, I'll write A by A minus X. I just inverted. This is logarithm A power anything. Logarithm A power minus 1 equal to minus logarithm A. Therefore, minus, and then this minus will get plus, becomes plus, and bt logarithm A by A minus X. This is K, right? What happens when you take one of the reaction, though it is second order reaction, it follows second order kinetics. When one of the reactant is taken in large amount, see, large amount, the rate constant expression becomes, compare this equation with the first order rate constant expression K equal to 2.303 by T logarithm A by A minus X. This is first order rate constant equation, you compare these two equations. B is constant, right? And also it is taken large amount. So due course of the reaction, the B will not change appreciably because it is taken very large amount. When the reaction proceeds, uh, the amount of B changes will be negligible. So this is B is taken as constant, right? Okay, then these two equations looks same, right? This is what I want to conclude, that when though it follows a second order reaction, when one of the reactant is taken in very large amount, then those reaction will follow first order kinetics, right? But if A and B taken small, uh, equally or small amount equally or small amount of A and B is taken to carry out this reaction, then this reaction of course will follow a second order kinetics. But one of the reactant is taken very large compared to the other, then this reaction will follow first order kinetics. And this type of reaction is known as pseudo first order reaction. Pseudo first order reaction, right? So very well known, pseudo first order reaction. Then I'll give I'll give an example. This is also very well known example for pseudo first order reaction. Ester, hydrolysis of ester using acid, mineral acid. And this is reactant. When water is taken very large amount of water is taken. See, if it is taken 5 ml, this will be taken some about maybe some 100 ml. Or if it is taken some 10 ml of ester, and water will be some about 100 ml. So when their amounts are different largely, then this is hydrolysis reaction, then the reaction supposed to follow first order kinetics. So I call this reaction as pseudo first order reaction, right? Next we derive uh, half-life expression. Half-life expression. So we learned half-life is time taken for a reactant to be completed 50%. I'll take this rate constant equation, 1 by t 1 by a minus x minus 1 by a. Here I substitute time is now t of x is a by 2, that half of the initial concentration that you are taken. A is the initial concentration. When a becomes half of its initial amount, then we call it as half-life period. This is product concentration. Then a by 2 is the amount of unreacted molecule at t of will be equal to the product formed. Product form, that is, if you take 1 mole, see, A is converted into product. This is 1 mole. Then time taken, conversion of 1 mole into half, half of its initial amount, that is 0.5 mole, is called a T of. Here at initially at 0 time the product is 0. Then how much product would have formed? The 0.5 mole is remaining, so 0.5 mole would have been converted into product. Therefore this is same, right? So this is A by 2, this is X. So our time T of X equal to A by 2. So if you substitute here, this is T of 1 by A minus A by 2 minus 1 by A. Then this is K equal to 1 by T of 1 by A minus A by 2 is A by 2 minus 1 by A. K equal to 1 by T, this is 2 by A minus 1 by A. This is equal to 1 by T A, sorry, this is T of. Therefore T of equal to 1 by K times A. This is for half-life expression for a second order reaction. You find that the half-life period is inversely proportional. So T of is inversely proportional to initial concentration. So if you take very small amount of if you take small amount of A, then the time T of will be very large. Then it will take more time for the completion of the reaction. Okay, that's all. Next, I will solve a problem.